All right, good morning, everyone. I'm back a little earlier than expected, so we won't have to delay until 11:05. We're going to start some review questions in just a bit, but the main topic of today will be starting and finishing the inequality section and interval notation. So today we will finish inequalities and interval notation. Interval notation. This was a topic that I should have covered yesterday, but due to the complexity of some of the questions we were doing, we had to shove it off until today. But it's a pretty brief section. And then the real topics of today will be relations and functions. Function notation. Domain and range of functions. And then graphical properties of functions. So a lot of topics. It's a little more packed in this section than I would like, but there doesn't seem to be a great spot to rearrange these topics. So it's better to keep them all self-contained as much as we can. And if we need to maybe visit some of these topics over 2 days, that is probably okay as well. Just like last week, if there's a topic that I don't get to today that I've put on your worksheet or quiz that's due Monday, that's the reason I have it due Monday at midnight, because ideally there's not more than one or two questions on either of those things that we haven't talked about. So we have afforded ourselves a little bit of flexibility in that regard. Okay, so let's just start off with a review question though. Let's try one of those other types of equations. This falls into the other type. So if I'm going to try to solve this question, what do you think the first step should be? Any thoughts in comparison to what we did yesterday?
Multiply by the common denominator.
Yep, the common denominator. And the first thing I do want to do in order to find that common denominator, though, is to fully factor everything. And if you look, this is a difference of perfect squares. So this is x, oops, not x squared, x minus 3 and x plus 3. And just like I have been saying, if you have an ugly quadratic in one of the denominators in this class, it should just factor to the other two linear terms in the other fractions. So then what we're going to do is multiply through by this common denominator. And this common denominator is x minus 3 times x plus 3. So x minus 3, x plus 3. And now we're just going to distribute this to every term we see in our equation. So when I start distributing that, I get 2x times x minus 3 times x plus 3 over the quantity x minus 3 plus 5 times x minus 3 over x plus 3 over x plus 3. And that's equal to 27 x minus 3 x plus 3. over x minus 3, x plus 3. So always remember to factor everything as much as you can. And in the section when we talked about solving rational equations, I did lay that out as one of the first steps, which is always factor as much as you can in every denominator of the equation. So the next step is correct to multiply through by the common denominator, but in order to see the common denominator, you need to make sure everything is factored. And now we can do some cancellation. So I can cancel this guy and this guy is a factor of 1. This guy and this guy is a factor of 1, and both of these as a factor of 1. And there have been a lot of patterns between these questions. Maybe not always as nice as this, but we usually get singular cancellation, singular cancellation, singular cancellation, singular cancellation, and then double cancellation. That's really been the trend. And that makes sense. So now we'll simplify this a bit. 2x times x plus 3 plus 5 times x minus 3 is equal to negative 27. And now what we have is not a linear equation, but a quadratic equation. This is 2x squared plus 6x plus 5x minus 15 is equal to negative 27. So I'm just going to start combining as many terms as I can. Here's 2x squared plus 11x. And then if I add 27 to negative 15, I should get positive 12. So how should we go about solving this quadratic equation? Any suggestions? There are multiple correct ways to do it. So can I factor this normally? Like, can I say this is x minus something, x plus something like this?
No.
No, right? Because this factor out in front of the x squared is not 1. So it doesn't factor as simply as this. But let's just factor it. We can factor it still, but we need to use factoring by grouping. So a times c is 2 times 12, right? That's 24. Now let's think of some factors of 24. 1 and 24. 2 and 12. 3 and 8. 4 and 6. And I think that's it. And if you look right here, I'm trying to find two factors that I can combine in some way, in some plus or minus way, or maybe both plus or maybe both minus to make 11. And that's this row right here. 3 plus 8 is 11. So bingo, that's what we want. So what do I do? I break up 11x as these two factors, 3 and 8, as 8x plus 3x plus 12 is equal to 0. And now I can do the factor by grouping. I can group these into two separate pieces and then factor out any common terms I see in each of them. In the left side, I can factor out not only a 2, not only an x, but a 2x to get 2x times the quantity x plus 4. And then I can factor 3 out here to get the quantity 3 times x plus 4. And just like I always say, these must match, and they do. These must match in order for this to work. They will always match if you've done the factorization correctly. If they don't match, you've done something wrong. So since there's an x plus 4 here and an x plus 4 here, I can factor out x plus 4. And I have 2x plus 3 equals to 0. So here, this gives me a solution of x equals negative 4. And then this one, we need to do a little bit of extra algebra with. If 2x plus 3 is equal to 0, that means 2x is equal to negative 3, which means x is equal to negative 3 over 2. So those are our solutions. We did forget to do one thing though. We needed to see what the restrictions are because we potentially can arrive at a solution that isn't valid that would result in division by 0 at some point. So um, let's see if I can zoom out instead. In this factorized form, what are the two exclusions we need in this equation? There's two values that we are not allowed to have as a part of our solutions.
3 and -3.
Yep, plus or minus 3, exactly. Because plugging in either of those numbers would result in division by 0 over here. But neither of these are division by 0 because neither of them are plus or minus 3. So these are two solutions for us. So any questions on this example? Okay, cool. So what I want to introduce now is something called interval notation. And interval notation is actually extremely powerful and used widely in math because often, for example, let's just say I told you x was exactly 4, but now, so this is an example. X is equal to 4. That's fine. That gives me an exact value. X is definitely 4. But what if I tell you instead X is something equal or greater than 4? So now, instead of an exact value, you have kind of a range of values. And the way we would write this is x is greater than or equal to 4, meaning this bracket right here. So the difference between writing an interval like this and this is this bracket means I can be equal to 4 or greater. Does everyone know what this symbol is? It's infinity, meaning there is no largest value it can take. If 4 is greater than or equal to 4, or if x is greater than or equal to 4, it could be 5, it could be 6, it could be 7 quintillion. It could be as big as I want, meaning there is no largest value it can attain. This is why we write infinity for the upper bound. So this bracket means inclusive of 4, so equal or greater than 4. This would be strictly greater than 4. Let's say I do something else. Let's say I say greater than 4, but less than 6. So now I'm not free to be a super big value like infinity. I need to write this in some type of interval notation. It's greater than 4, so I know the bottom value is 4. And then it goes all the way up until 6, but it's less than 6. So it can't be exactly equal to 6. So this is an interval. If I were to draw it on a number line, it would look like this. Here's a number line x. Here is 4 right here. And here is 6. This interval describes this region right here. So any number in between here is okay. It's between 4 and 6. So I think some students get confused in how we write intervals and then x and y points in the same way. But really, it depends on the context of the question. So then let's try another one. Let's say I do greater than or equal to 4, but less than or equal to 6. So this is similar to this one. So we can think about how to change this interval. What does the added verbiage make this new interval right here? So instead of these parentheses, meaning 4 and 6, meaning I can't exactly include 4. The exact number 4 is not included in this interval. Everything slightly greater than 4 is included. So 4.000000000 dot 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 1 is okay, but not exactly 4. Same with 6. It can be 5.999999999, but not exactly 6. This is why it's greater than 4, but less than 6. But now, since I can be greater than or equal to 4 and less than or equal to 6, all I need to do is transform this and say, okay, brackets 4 and 6. This means that the boundaries are included. 4 and 6 are a part of the solution. And the way I would draw this on, say, for example, a number line is now instead of these open circles, meaning I can't quite exactly have 4 and 6 in my interval, I'm going to have them with filled in circles. And this is the solution set that's described. So notice this describes a single interval, but now let me see if I can split it up a bit. I'm going to say less than or equal to 4, but greater than 6. So let's draw this on a number line. Less than or equal to 4, well, that means I should have a closed circle where 4 is. But is less than or equal to 4 this direction or this direction? Here are all the numbers less than 4. So it's this, it is this region in this direction. It's less than or equal to 4. So that little portion describes this direction. But then in the second part, it says greater than 6. So instead of a closed circle, I need an open circle because it doesn't say greater than or equal to 6. It's strictly greater than 6. So here I have 6. And greater than will point this direction. Here are all the numbers that are greater than 6. 7, 8, dot, 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 all those numbers. So now, how do I describe both of these intervals? Because now I don't have these connected intervals. The lowest value isn't 4 and the highest value isn't 6. It goes from negative infinity to 4, and then it drops off and disappears, and then repicks up at 6 to infinity. And the notation for that is called union. I'm going to say it's negative infinity to 4 brackets, because I can include 4, union parentheses, because I can include 6, 6 to infinity. This describes this range right here. Any questions so far? So then let's try one more. Let's say I said all possible real numbers. What do you think that would look like in interval notation?
Positive infinity,
So that would be the largest value you can take, but what about the smallest value?
negative infinity.
Exactly. So the interval is negative infinity to positive infinity. This describes all real numbers. So it can be super negative, super positive, it could be zero, it could be one half, it could be two halves, it could be 8 million, it could be negative 7 billion, anything. Any possible number. So we can actually have equations involving these type of things. So for example, if I wanted to write x is something greater than or equal to 4, this is how it'd be written. It would be x is greater than or equal to 4. This would be x greater than 4. So this added line at the bottom of this, what kind of looks like an arrow, means it's free to be that value. It could be exactly 4, or anything greater. This is strictly greater than 4, meaning it can't be exactly 4. This would be 4x less than 6. So x is greater than 4, but less than 6. This would be 4 less than or equal to x, less than or equal to 6. This would be x is less than or equal to 4, and this would be x is strictly greater than 6. So since we have developed a notation that allows us to write x in some way in how it's related to numbers, now what we could do is solve equations to solve inequalities like this. So you can think of inequalities, maybe I'll write this down. Think of inequalities as a relaxation of equalities. So instead of an exact solution, like x equals 3, we get a range of solutions. So maybe x isn't exactly 3, but it's anything greater than 3, or anything less than 3, things like that. So the big difference, though, is now what we have to do is, when we had equations like this, we were free to, add or multiply anything we wanted, so long as we did it on both sides of the equation. And that will still hold true for inequalities, so equations involving inequalities, but there are some rules that will be slightly different. So let me tell you those rules. If I know a is less than or b, or less than b, that's how I say it. If a is less than b, then what I can do is add both sides. I can add c on both sides, and the inequality remains the same. So I don't change the inequality by adding something to both sides of an inequality equation. But here's the important one. So if a is less than b, then a times c will still be less than b times c, if, so this is where it's important. If C is a positive number. So this is really easy for us now. So I didn't have to write this in words. I could say C is a positive number, which is a super useful thing to say. But now, if I do the same thing, what will happen is the direction of the inequality flips. So this has flipped now to the pointing to the other direction. If C is a negative number, that's what that means right there. C is less than 0. So if I am doing algebra with an inequality and at any point I'm required to multiply by a negative number or divide by a negative number, which technically is the same thing as multiplying by a negative number, I need to just flip the inequality. And that's really all the algebra that we need in order to solve inequality equations. Maybe I'll put this as A. So these are rules worth remembering, mainly because you'll be doing it a lot. So let's try it. I know x minus 11 is less than 26. So let's find the range right here. In order to solve for this, I want to get x alone, just like a regular equation. So I'm going to add 11 to both sides. Do this in a different color. I'm going to add 11 to both sides. So do I need to flip this inequality at all?
No.
Nope, exactly. Because this rule says whether it's negative or positive, remember I didn't have to divide this up into two separate things. If so I can add or subtract any number I want on the side of an inequality and the direction doesn't change. So I know x, if x minus 11 is less than 26, certainly x must be less than 37. And I can write this in interval notation as well. So I always viewed this less than symbol as an arrow. The arrow points that way. So it's less than 37. So let's isolate x again. So what I'm going to do is subtract 14 from both sides to get negative 12 is greater than or equal to x. And the easy way to rewrite this, I think, is if you were to just reverse everything, this is the same thing as that. If I read it this way, x is less than or equal to 12, or sorry, x is less than or equal to negative 12, or negative 12 is greater than or equal to x. X is less than or equal to negative 12. Just because this is just a much more pleasing way to write the solution. If you're totally okay with this, I don't mind it either, but I prefer that. It just looks nicer to me. So that's all the numbers that are less than or equal to 12. Let's try this. So this is the first equation or first example that I'm going to have to divide or multiply by something. So over here, I'm going to divide by 9. That'll give me x is greater than or equal to 4. So I didn't give you a separate rule though for division, because this rule for multiplication is basically a broader rule than division, because division in a way is the same thing as multiplication. What did I do over here? I multiplied both sides by 1 over 9, right? Dividing by 9 is the same thing as multiplying by its reciprocal. So I don't need a separate division rule because it's the same thing as the multiplication rule. And so when I divide by 9 or multiply by 1/9, since 1/9 is greater than 0, the inequality does not flip. This rule says right here, if this number is greater than 0 that I multiply by both sides, the inequality will remain the same. If A is less than B, A times C is less than B times C. So X is greater than or equal to 4, meaning where does the arrow point? It starts at 4, inclusive of 4, and it goes off forever into infinity. But now what about here? Notice the only addition is I have this negative. So what happens?
The signs change.
Yep, the signs change, meaning the inequality will flip. So instead of being greater than or equal to 4, it will be less than or equal to -4. So it's -4 because 36 divided by -9 is -4. But because I had to multiply by 1 over -9, the inequality reverses direction. And that's our solution set. So let's try a couple more examples. We have a lot to talk about today. So here's a new type of example where we have x's on both sides of the equation. So we will solve this much like we have regular equations. I'm just going to distribute and simplify both sides as much as I can. And now, notice right here, though, all I have is sum or differences of terms currently. So I can rearrange terms in this inequality as much as I want for free without risking changing the sign at all. Whether I'm subtracting or adding to both sides is irrelevant in terms of does the sign flip. The only time I need to be careful of the sign flipping is if I am dividing or multiplying by something. So the fact that I have x over here and x over here is fine because I can bring both x's to one side of the inequality. I can very easily do that. I can do -6x, -6x to get 2x plus 3 is greater than 3. Didn't even have to think about whether the sign flipped because I'm simply adding or subtracting something. Same thing over here. I'm going to subtract 3 and subtract 3 to get 2x must be greater than 0. So this is kind of weird. So let's think about this intuitively outside the realms of math or outside the realms of this notation. I have a number 2 and an unknown number x, but I know that when I multiply 2 and this unknown number, the resulting number is greater than 0. So what must x be? X has to also be a number greater than 0. That's the only issue, right? It can't be 0 because this product can't be exactly 0. But if I multiply 2 by any number that's greater than 0, the resulting number is greater than 0. We don't actually need to think that broadly, but I'm just trying to give you guys an intuition for how this works. I can divide both sides by 2 without switching the sign to get x must be greater than 0. And that's exactly what I said. X must be some positive number, a number greater than 0. Okay, so now we're going to talk about compound inequalities. So as an example, 3 plus x is greater than 7x minus 2, which is greater than 5x minus 10. So this has two sides now. And what we can do to solve this actually is separate them as two separate sides. I can solve this inequality and this inequality. And this will give me the correct solution for this question. This is how I recommend doing it. I think it's just easier this way. So I get 3 plus x must be greater than 7x minus 2. And 7x minus 2 must be greater than 5x minus 10. Is everyone clear on where I'm getting these two different inequalities? You can just give a thumbs up if you want.
Yes.
Great. And now I can just solve these as two separate problems. And that has been the motif in a lot of the things that we've done in this class so far. I've added additional complexity to a question, but now what we do is we provide the tools to reduce that additional complexity to a form of a question that we know how to solve. So right now we had this compound inequality that was difficult. What did we do? We broke it up in a way that now we have two simpler inequalities that we do know how to solve. So that's how math works. You start with a complicated, really simple topic, and then you go, what if it was a little bit more complicated? And then you figure out, how can I reduce it to something that's simpler? Then you go in an additional level. How do I make this problem even more complicated? And then you reduce it to something that was slightly less complicated, reduce that to something that's slightly less complicated, and go from there. So let's solve this. I'm going to subtract x from both sides to get 3 greater than 6x minus 2. Then I'm going to add 2 to both sides to get 5 is greater than 6x. And then I'm going to divide by 6. So 5x is greater than x. 5 over 6 is greater than x. Or x is less than 5/6. That is the reversal of the notation that I've shown you. It's just much easier to read this out. X is less than 5/6 rather than 5/6 is greater than x. Do the same thing over here. I'll subtract 5x out. Then I'm going to do 2 lines of arithmetic on one line. Here I have 2x is greater than -8. I'm going to divide by 2 to isolate x. Do I have to flip the sign?
No.
No, right? Because I didn't multiply or divide by a negative number. I did it with a positive number, so the sign will remain the same. So x is greater than -4. So now what I'm going to do is recombine these as a single solution set. And it's kind of confusing because is this going to be -4 to 5/6 or negative infinity to -4 union 5/6 to infinity? Does anyone have a guess? Which of these two will it be? The first or second?
First.
Yeah, it's going to be the first. So the trick is with this compound inequality is both of these must be true at the same time. So these are two possible contenders, but if you want, and I really struggled with this when I was taking this math, what I would always do is just write it out. So here is -4. And I know x must be greater than it. Here is 5/6. And I know x must be less than it. So if these two arrows are pointing to each other, what you have is a single interval, which is this one. If you, for example, get these arrows are pointing away from each other, it would be this one. This is what we call disjoint intervals, meaning they don't touch each other. They are they are separated by some piece. So in previous semesters and when I tutor this, I do explain another technique to solve these, but honestly, this is probably the more straightforward one that will always work and always be nice for you. So this is the technique you want to know. So if you get a compound inequality, just break it up into two individual inequalities and then solve. Just make sure to reconvene at the end and don't write your solutions like this. This are the two solutions, but they need to be true at the same time, meaning you need to do this type of analysis. Are they going to be disjoint like this and point in different directions? Or will they be describing like a bubble of numbers? Okay, so in terms of inequalities, I think that's all I can do for now. We can talk about some more on Monday as well if you guys are struggling with anything on the worksheet or your homework. But for now, we should move on to the next topic. So then I'll just bring this down as a reminder for us. Give me just a second to pull this stuff up. Okay, so what we're going to talk about now are functions. Functions are, I know I say this with every topic that we do, but probably one of the most important things in mathematics. That's why math is so cool, right? Because everything is so important. Everything has been building off of each other, so everything is important. So a function, f, so f is a function. They were not very creative with the choice of letters for function. F for function is very unoriginal. But at its heart, what a function does is takes in an input, x. So this is my machine. This is my machine. And this is my input. Here is x. Machine. I'm going to draw this a little bit more like this. So x is a set of numbers. It's some type of input that I'm allowed to put into the machine. And inside the machine is a function. And what that function does is it transforms my original thing that I put inside to a new value called f of x. At its heart, that's what it is. And now what we can do is talk about what classifies something as a real function. And here is the big thing. So here are all of my inputs. And here are all of my outputs. So I'm not going to write the machine, right? I'm not going to write f. Here are my outputs. So I'm going to copy this so I can have a couple of different examples. So say I have this number p, this number q, and this number r. And what I'm going to do is draw arrows in how they relate to my outputs. how they relate is through the function, but we don't need to really write that intermediate step to understand this point. And say I have two different outputs, m and n. When I plug in p into my function, it outputs m. When I input q into my function, it outputs n. When I put r into my function, it outputs n as well. So I have three sets of numbers that only have two possible outputs. This is still technically a function. This is classifies as a function. Same thing with this. So inputs and outputs. If I have P, Q, and R, and then X, Y, and Z, and I have this type of relationship, this is also classifies as a function. Or it could be that P, Q, and R all get mapped to X, meaning when I put P, Q, and R into my function, it gives me the same output X, no matter what. But I've given you two examples of what would classify as a function. This relationship is a function. But now I'm going to show you an example that does not classify as a function. And this is the important one. Oh no, I don't have my copy and pasted images anymore. Input, output. Here is P and Q, X, Y, and Z. So we can have two different inputs going to the same output. That's okay. But I cannot have one single input go to multiple outputs. That is actually what breaks a functional relationship. Not a functional relation. Because if you think about it, so say I had this machine again. So here's my machine F. And when I input X into it, I need the output to go into different types of bins. Right? This is like some type of factory machine. And we have different bins. X, Y, and Z. So it's going to go into one of these. But so say I input Q into this function. I put this Q in. It gets transformed by the function. But now, since this relationship says, oh, Q should become Y, so should I put it in the Y bin? Well, that's a problem because Q also says that it should be Z. So it should also be in the Z bin. It can't go to both bins. It has to go to just one bin. So that's why, for example, this is still a relationship, a function relation, because if I put Q in, it says it should go into the N box. If I put R in, it should go into the N box. Two inputs going to the same bin is fine, but one input going to two different bins is not okay. Does everyone understand this analogy? You can also just give thumbs up.
Yes.
All right, great. So let's just try some examples right here. we can think of some really basic relations as just inputs and outputs. So I'm going to say input, output. -3, 5, 7, 4, 4, -3, 1, and 4. So does this represent a functional relationship? I shouldn't say functional relationship. I should say function relation. Does this represent a function relation? Any ideas how we would think about it? So if I were to put these numbers in bins, right, these are all different numbers. 3 will go to 4. 5 will go to -3. 7 will go to 1. And 4 will also go to 4. Or it can go to that one. Actually, no, I'm sorry. It can't go to that one. The way this table is written is 4 cannot go to this 4 up here. So this is a functional relationship. Function relation. And the easy way to tell whether it's a function relation, so you have some homework on this, is if you don't have any repeats of inputs, then it's basically guaranteed to be a function relation. So let's do another example. So I have 0, -5, 3 and 7, 0 and 2, 6 and 4. So right away, you see these repeats right here. So 0, the same input goes to different outputs. So this is not a function relation. I plug in 0 and it says it should go in the -5 bin. But then over here it contradicts itself. It says 0 should go into the 2 bin. That's the contradiction. Here it says -3 should go into the 4 bin. That's okay. Here it says 4 should also go into the 4 bin. That is also okay. Okay. Sorry, my mouse died. So instead of, actually, I need to introduce this verbiage now. So I'm going to say definition. The domain is the set of all possible inputs. The range is the set of all possible outputs. So these are important concepts because I'm going to be referring to what domain and range is all the time, because it's an important concept when we get into analyzing functions. I want to say, okay, here's a function, but what are the numbers I'm allowed to plug in? What is in this bin right here? That's the domain. this is the range. This is the all of the output. So let's just look at these examples up here. The domain of this example are these numbers right here. -3, 5, 7, and 4. And I shouldn't write it like this. I should write it with these curly brackets. These curly brackets means it's just a collection of elements. It's just a bowl of numbers rather than ordered pairs or intervals. It's just some numbers. Here's the domain. And down here, the domain is 0, 3, and 6. I don't have to write 0 twice. Down here, for the range of this example, it's 4, -3, and 1. I don't have to write 4 twice. For this one, the range is -5, 7, 2, and 4. So let's try another type of example where we have pairs of numbers. So these represent X and Y values, where X is the input and Y is the output. So that means these X values here make up the domain. It's going to be 4, 7, -10, and -8. Those are all the unique numbers. And the range will be 9, -3, 6, and 5. Okay, so I have to kind of keep chugging along right here. If you guys are struggling with this section on the homework at all, please do not hesitate to reach out to me and we can discuss it, or we can shove it off until next week to really go about it. Okay, so let me just pull up the next section real quick. So I just kind of wanted to ease into the segue. When I write a function like this, so we're going into function notation. This right here is actually a function of X. We've been dealing with functions this entire time secretly. Here's a function. Here's Y, and here's X. So what I can do is I can input an X and I get a Y out. That's exactly what a function does. It takes in an X, transforms it in some way, and gives me an output. In this case, all of the outputs lie along this line. So what I could do is, instead of writing this function like this, as y equals 3/4 x minus 2, I could write it as f of x, which is 3/4 x minus 2. This is still valid. And this is why when I say y or f of x, we're talking about the same thing. It's just now we've added this additional notation. When we're talking about the Cartesian coordinate plane, we can say y is the same thing as f of x, because we're always going to be talking about some function on the Cartesian coordinate plane or some line or curve, and that will always be f of x, but that will always be the same thing as y. So now what we can do is analyze this in a maybe slightly more succinct way. So let's say I have this curve, and this is f of x, and this is x. Here is 1, and 4, 2, and 5. This is 4. And now I can tell you, or I can ask you questions about this function. What would be f of 1? So how do I think about this? This is me plugging in x equals 1 and seeing what f of x is at x equals 1. This is the shorthand notation for it, f of 1. So let's do it. If I take in x equals 1, what is the output? I'm going to trace that output all the way up to the function. This y value is the output. So f of 1 is 4. Let's look at 2. What is f of 2? Any suggestions? F of 2 will give me 5, right? I go to 2 right here, and I'm going to take that value and plug it in. When I plug it into a function, it will go up and provide me the value of 5. Let's think about where is f of x equal to 4. So now this is a question about at what x is f of x equal to 4. And I'm going to have two solutions for that. What values of x? Where, at what values of x is f of x equal to 4? Well, f of x is equal to 4 at x equals 1 and x equals 4. So this is a reversal of the direction. When we were doing these types of questions, we went to a certain x value, went up, and found the y value. Plugged in 4, went up, find the y value. But when I ask, okay, now where is this function equal to this number, we look at that number and then go down. Look at that number and then go down. So that's at x equals 1 and at x equals 4. So that's basically the functional notation. Let's see here. Is there anything else in this functional notation I need to write? So if I give you this equation right here and say x minus 8y cubed is equal to 0, and I said express y as a function of x, of x. All we need to do is rearrange and solve for y. I want to write y equals something about x, a function of x. So this is a y written as a function of x, meaning if I plug in some x, I get an exact y value out. So if I plugged in 0 into this equation, I would get 0 out from y, or 0 out from f of x. So there's a really great test to figure out whether a graph truly represents a function. It is called the vertical line test. So if I have a function right here, here is f of x, x. And if I draw a vertical line through it, and notice I didn't specify where, meaning anywhere on the graph, I can draw a vertical line and it only touches the function once, it is a function. If a vertical line could be drawn through any point on a graph, the graph is a function. We might not know the equation of that function, but it is a function. So as a counterexample, I'll use a different color ink. So say this is a separate new graph. I can draw a line through it, but notice this line intersects the function twice. So this is not a function. It fails the vertical line test. And let's think about this intuitively. Back to those diagrams that we had above. What was the issue with something being not being a function if the same x input gave me two different outputs? So keep that in mind. Now let's go back to this graph. The same x input gives me two different y outputs. If I plug in this value x into this function, should it give me this y value or this y value? It points to two different bins, so it can't possibly be a function. Any questions on that? So let's see, what else do I need to discuss today? We get function notation. Function notation, domain and range of functions, graphical properties of functions. Okay, so I think we can probably finish some of the domain and range of functions. So let me pull that up. The last topic, I guess we will push to next week because I am desperately running low on time. Domain and range of functions. So I'm just going to give you some graphs and we can talk about the domain and range pretty easily. It doesn't seem to want to draw the curved line. So we'll put this at like -3. This will be +2. Here's x. Here's f of x. Here is we'll say up here is 5. And then over here is like maybe -2. So then here's 1. Okay, and so not drawn to scale. 2, 1. Yeah, really not drawn to scale, but that's okay. We don't need it to be drawn to scale to correctly think about this. So the range of this graph Well, first, let's ask, is this a function? We could really easily tell through the vertical line test. Do you guys think this is a function? So it is a function because if you look anywhere on this graph, no matter where I draw this vertical line, it only touches the graph once. If this graph started curving in on itself again, then I could say, oh, I could draw a vertical line here, and it would fail the vertical line test. So the range now, so it is a function, and the range is all outputs. But this graph doesn't need to be exactly 4, exactly 3. It could be any number in between 4 and 3, any number in between 2 and 3, any number in between 1 and 2, any number in between 1 and 0, any number between 1 and, I'm saying this highest value is 5 right here, and this lowest value is 3. And that's exactly what we're going to do. We're going to use interval notation now to describe range and domain. The lowest value this y value can attain, the f of x, right? The all the possible outputs. So all of the outputs exist on this axis. All the inputs exist on this axis. The highest value it will ever get is 5. And I'm just going to make this dot bigger because I wanted to tell you that the highest value it attains, the peak, is 5. So it is inclusive of 5. It reaches 5. Well, let's go down here. With this open circle, does the lowest value actually become -3, or is it almost -3? So since I have the open circle, what I'm saying is it's almost -3. It doesn't actually reach -3. Let's think about domain. So domain is all of the possible inputs. So it looks like that's going to start at -2. And since I have this dark circle right here, I'm going to include -2. I can plug in -2. But if I continue along this axis and I get to +2, I actually can't find a correct input right here. It almost reaches -2 or +2. So it's 2 parentheses. Let's try another one. Oops. So these arrows are just a way to write that this goes on forever. It's just, I can't draw it going on forever. So contrast the difference between this one and this one. This one just stops clearly here, meaning I can draw this like box around my function. But this means that the function will just continue on forever without bound. We can't see what happens. So let's use that idea. The domain. What do you think the domain is for this function? So this function,
infinity to positive infinity.
yeah, exactly. Because this function goes on forever. And while we can't see it, it will just continue to go like that forever. We can't see it go that far though. So the domain is all possible real numbers. You can say -infinity to infinity, or you can also use this notation. This is all real numbers. But let's think about the range. So the range does not go forever in either direction. And if I'm talking about strictly just the vertical direction, it never goes less than -2. The function can increase as much as it wants, but it can never drop below this value. It's not going to suddenly turn back down and go below. So the range is inclusive of -2 to infinity. The range only begins here and then can go increase as much as it wants. Okay, so I want to maybe do one or two examples of when we're actually given equations of functions to find the domain. But don't take it too seriously because I want to talk about it in a more strict and maybe more complicated way on Monday. So if you see that on your homework, feel free to just ignore it for now and finish that homework when we've done it. But same for the quiz and the worksheet. So if I give you this function right here, so I'm going to stop writing y equals something. It's going to be understood that f of x is the same thing as y. So what was the restriction of square roots when we're talking about real number solutions, meaning not complex solutions? What was the restriction? The restriction was I was not allowed to put negative numbers inside a square root. I could put 0 inside a square root, but not negative. So let's write that in interval notation. Whatever is in here, all I know it has to be greater than or equal to 0. It can be equal to 0, but it has to be greater than, or it has to be non-negative. And what is that thing inside the square root? It's this guy. And now I can solve this inequality. What I'm going to do is add 2x to the other side of the equation, divide both sides by 2, and then just rewrite this in a slightly more way, easier way. So this is the domain. This describes all possible inputs that I'm allowed to put into the function. What did I have to restrict myself to? I knew that whatever was inside my square root had to be greater than or equal to 0. So we set that equation up. And now I've given you a range of all, maybe I shouldn't say range. I've given you a group of all possible numbers that I could plug in here and not get some ugly contradiction. And here's the domain. The domain is -4, negative infinity to +4, inclusive. Oh, why did I write 4? I'm sorry. This should be 9. Hopefully everyone is clear on that mistake. So now, let me change it up. Let me put this inside the denominator. So I still have that same restriction. I know that this has to be greater than or equal to 0. But since this is now in the denominator, I need to be extra careful of the restrictions. Can I have the square root of 0 down here? So the square root of 0 is 0. And if I did that, it would be division by 0. So instead of this inequality being greater than or equal to 0, I'm going to make this inequality strictly greater than 0. And you're going to do the same thing and say, this is strictly less than 9. So this domain is negative infinity to 9. So this is the domain. So that is all I have time for, unfortunately. There was some other stuff I really wanted to talk about, but we will push that off until Monday. Hopefully, I'll take a look at it. Everything is due Monday, so it's not a big deal that we didn't finish everything. We still have some time on Monday. But if there's like a lot of content that would be kind of unreasonable for you guys to do in an afternoon before it was due, I'll take a look at it and maybe we can push it off another day. But just try and finish as much as the quiz and the worksheet as you can. And then when we finish these last topics on Monday, you just knock those out and submit it. So other than that, have a great weekend.